Good day everyone, I am Hessie and welcome to this video lesson on one of the most important tool in number theory, the extended Euclidean algorithm or the EEA. If you ever wondered how to solve the equation like ax plus by is equal to GCD a and b, or how to find the modular inverse used in cryptography, this lesson will guide you step by step, and I promise to make the process simple, clear, and very doable. And by the end of this video, you'll be able to perform the extended Euclidean algorithm confidently. So let's get started. Now, what is extended Euclidean algorithm? So before we jump into the steps, let's review what is the EEA or the extended Euclidean algorithm actually is. So you probably know the Euclidean algorithm, and it helps us to find the greatest common divisor of two numbers using repeated division. And the extended Euclidean algorithm takes this one step further. It is not only finds the GCD, but it also gives us the integer x and y such that ax plus by is equal to GCD a and b. And this is extremely useful when solving linear equation, finding modular inverses, and working with cryptography like RSA. So think of the Euclidean algorithm as Euclid but with bonus features. So for us to know how to solve this one, there are steps for the extended Euclidean algorithm. So the two parts of this is the forward process and the backward process, or the forward process and the backward process. So the extended Euclidean has two major parts, as what I have said: the forward process, the Euclidean algorithm, where we perform repeated division for us to get the GCD, and each time we divide, we write the remainder. And the second is the backward process, or the backward substitution. So once we reach the last non-zero remainder, we go backward, expressing each remainder in terms of the previous equation. So this is how we get the x and the y in the equation, which is ax plus by is equal to GCD a and b. So let us apply this in real example. So our first example is to find the GCD 56 and 15 and express it as 56x plus 15y. So with this, we will apply the forward process. So let's start with dividing. So let's divide step by step. So we have first the 56, which is equal to 15 times 3 plus 11, and 15 is equal to 11 times 1 plus 4, and 11 is equal to 4 times 2 plus 3, and then 4 is equal to 3 times 1 plus 1, and 3 is equal to 1 times 3 plus 0. With this, once we reach the remainder of 0, that's where we stop. The last non-zero remainder is, in this solution, is 1. So our GCD is the GCD for 56 and 15 is 1. Now, we will, because we have now our GCD, now we will perform the backward substitution to express that one GCD as a combination of 56 and 15, and for us to know the X and the Y. So let's start. With the equation that gives us the remainder 1. So let's start with the step number 4 in our forward process, which is 1 is equal to 4 minus 3 times 1. And then we will replace 3 using the step 3, and which is 3 is equal to 11 minus 4 times 2, and we will plug it in to 1, which is 1 is equal to 4 minus 11 minus 4 times 2, and then it will become 1 is equal to 4 times 3 minus 11. And we will replace 4 using the step number 2, which is 4 is equal to 15 minus 11 times 1. And then we will substitute. In substituting, we will have 1 is equal to 15 minus 11 times 3 minus 11, which is also becomes 1 is equal to 15 times 3 minus 11 times 4. And we will replace 11 using the step number 1, which is 11 is equal to 15 minus 56 minus 15 times 3. And then lastly, we will substitute again 1 is equal to 15 times 3, and then minus by 56 minus 15 times 3 times 4, and then we will distribute it. So in distributing, we have 1 is equal to 15 times 3 plus 12 is equal to 56 times 4, and then 1 is equal to 15 times 15 minus 56 times 4. So the final form is 1 is equal to negative 4 times 56 plus 15 times 15. Thus, everyone, our solution, so here it is, our final answer, 1 is equal to negative 4 times 56 plus 15 times 15, which is our solution, is shows that x is equal to negative 4 and our y is equal to 15. So that is our example number 1. Now let's proceed with example number 2. So we have here, so the final answer is the GCD is equal to 1, and then our x is equal to negative 4 and our y is equal to 15. Now let's proceed to the next example. So for our next example is to solve 84x plus 33y is equal to GCD 84 and 83. So for our next problem is to find x and y such that 84x plus 33y is equal to the GCD of 84 and 33. So for our second example, we'll go a bit faster. So we will apply the forward process, and then the process is 84 is equal to 33 times 2 plus 18, and 33 is equal to 18 times 1 plus 15, and 18 is equal to 15 times 1 plus 3, and 15 is equal to 3 times 5 plus 0, which is our GCD for the 84 and 33 is equal to 3. Now, let's proceed with the backward substitution. So we will start with 3 is equal to 18 minus 15 times 1, and 15 is equal to 33 minus 18 times 1, and for the step 2, which is 15 is equal to 33 minus 18 times 1, and we will now substitute it. So for substituting, we have 3 is equal to 18 minus 33 minus 18 times 1, and then 3 is equal to 18 times 2 minus 33. And from step 1, we have 18 minus 84. 18 is equal to 84 minus 33 times 2. And then we will substitute again. For substituting, in substituting, we have 3 is equal to 84 minus 33 times 2 times 2 minus 33, which is equal to 3 is equal to 84 times 2 minus 33 times 5. So our solution is that x is equal to 2 and our y is equal to negative 5. So now let's proceed with our last example. Example number 3. Which is our example number 3 is to find the inverse of 7 mode 26 using the extended Euclidean algorithm, meaning we want 7x is equal to 1 mode 26. So which is the same as 7x plus 26y is equal to 1. So we will apply now the forward process, which we have 26 is equal to 7 times 3 plus 5, and then 7 is equal to 5 times 1 plus 2, and then 5 is equal to 2 times 2 plus 1, and 2 is equal to 1 times 2 plus 0. And our GCD, so our GCD is equal to 1, and 1 is 1 means that the inverse exists, everyone. So 1, the GCD is equal to 1, so the inverse exists. Now let's proceed with the backward substitution. So for the backward substitution, so we will start with 1 is equal to 5 minus 2 times 2, and then 2 is equal to 7 minus 5 times 1, and then we will substitute 1 is equal to 5 minus 7 minus 5 times 2, where it become 1 is equals to 5 times 3 minus 7 times 2. And from the step 1, we have 5 is equal to 26 minus 7 times 3, and then we will substitute it. It become 1 is equal to 26 minus 7 times 3, and then 3 minus 7 times 2, which lead to 1 is equal to 26 times 3 minus 7 times 11. Thus, our x is equal to negative 11. So to convert the mode 26 positive, then negative 11 mode 26 is equal to 15. So the inverse of 7 mode 26 is equal to 15, everyone. So ito. So the inverse of 7 mode 26 is equal to 11. Negative 11 mode 26 is equal to 15. So let's summarize everything that we have tackled today. So we learned today that number 1, the extended Euclidean has two parts, which is the forward, in which we find the GCD using division, and the backward process, in which we find the x and y through substitution. And then another lesson that we learn is we can always write GCD A and B is equal to AX plus BY. And third is if the GCD is 1, and then A has a modular inverse mode B. And lastly, the steps may look long at first, but with practice, everyone, they become very systematic and easy to follow. So if you understand today's 3 example, you are now ready to solve more complex number theory problem. And that concludes our lesson on extended Euclidean algorithm, and I hope this detailed walkthrough help you understand the steps clearly, especially the backward substitution part. And if you found this lesson helpful, don't forget to follow for more lessons and share with your classmates, friends in studying number theory. Thank you for watching. See you in our next lesson.